Welcome to geometric problems. So the idea here is we're looking at geometric problems in the coordinate plane. So we're looking at geometric problems in the coordinate plane. Typically dealing with tangent lines. And so the tangent lines themselves involve a derivative for the slope. So tangent lines use the derivative as slope. And so we get a differential equation. And can solve the equation for our original y. So we can solve for the original curve. So in our first example, or our only example, we're going to find a curve such that the tangent line at every point x naught y of x naught has y-intercept x naught squared. So we want the tangent line at every point. So the first trick is to just find the general equation for each tangent line. So the first thing we'll want to do is find the general equation for each tangent line. So find the general equation for a tangent line. To the curve. At x naught, y naught, or x naught, y of x naught. So again, we know that the slope would just be the derivative. We know that our point we have, so our equation becomes y is equal to our initial y value. I'm actually going to just write these as y naught instead of y of x naught. Technically, for a curve, it doesn't have to be a function. So let's shorthand this just to y naught. So our equation y is equal to y naught plus our derivative y prime at that x naught, y naught. And then times x minus our x naught. So this is our general form. And then we are told that the y-intercept, we have the point 0 x naught squared. So what this means then is we have x naught squared is equal to y naught, or y of x naught, plus y prime of x naught times 0 minus x naught. So we have x naught squared is equal to y naught minus x naught times y prime of x naught. Now I'm going to go back to the more broad notation. Y naught is equal to y of x naught minus x naught times y prime of x naught. We are told that this is true for every x naught. So this is true for all x naught. And so we can just replace x naught with x. And so if we write this as just x squared is equal to y minus x times y prime, that's essentially what we have just found as our equation. So our job from here now is to solve the differential equation. So now solve x squared equals y minus x times y prime. So the first thing I want to do is just rewrite this in general form. So we can rewrite this as x times y prime minus y is equal to negative x squared. This we can then rewrite as y prime minus 1 over x times y is equal to negative x. This is a linear, non-homogeneous first order equation. The first thing we need to do is find the homogeneous solution. So y1 is e to the negative integral of p of x dx, where our p of x is negative 1 over x. So y1 is e to the negative integral of negative 1 over x dx, or y1 equals e to the positive integral of 1 over x dx. This becomes e to the natural log of the absolute value of x, or just x is what we can pick as our y1. Next up, we're going to run variation of parameters. So we have our right side of the equation was negative x. And that's our g of x. So we had u prime was equal to g of x over y1. So u prime is negative x over x, or u prime is negative 1. So again, here we're assuming y equals u times y1. So our u prime is negative 1. That means u should be the integral of negative 1 dx, or u is negative x plus c. Then what we get is our y is y1 times u. Y1 was x, so y is x times negative x plus c. And we get y is negative x squared plus c times x. So presumably for any curve in this family, every tangent line has y-intercept at x naught squared.